Yeah, hopefully we have our paper and our pen in front of us so you write this down because it's useful information. Probably. We talked about rational numbers before. Rationals related to ratio. A ratio in math is what? Starts with an F. That too. Fraction, your favorite math F word. Yes, fraction. It's a fraction. We all freaking hate fractions. So, a rational function is a fraction. Specifically, it's a fraction with a polynomial numerator and a polynomial denominator. Poly on top, poly on bottom. That's a rational function. Yeah, we've already seen a couple of these. For example, one of our toolkit functions. We called that the reciprocal function. That is a rational function. This is the A0 polynomial. This is the A1 polynomial. X to the first power, x to the 0th power. We know what that looks like, too. Who remembers what the reciprocal function looks like? I see you doing this with your pen. So like this. Yeah? Okay. Is that it? He's shaking his head no. What are we missing? Good. It's both, because when x is negative, 1 over x is negative, so we're in quadrant 3. When x is positive, 1 over x is positive, we're in quadrant 1. Hmm? So what we're going to do today is talk about the domain of general rational functions, and then we're going to look at some properties. So first, let's talk about the domain of a rational function. So first, remember that we assume the domain is all real numbers. And then we look for problems. In fractions, functions where there is a variable in the denominator, what am I not allowed to have in the denominator of my fractions? 0. Can't divide by 0. Zeros are no-no. So the second step is I am going to set the denominator equal to 0 and solve for x. Very good, Bruno. What we're finding in step 2 are the no-no zones. What values of x am I not allowed to have? And those are where the denominator is 0. The reason we're doing rational functions now is we just spent like 2 weeks talking about how to find the zeros of polynomials. That's what step 2 is. So all of those skills we just practiced about finding zeros of polynomials, how to find the rational zeros, how to find the complex zeros, how to find the irrational zeros, how to use the quadratic formula. That's why we practiced it, because that's going to tell us where I can't have my rational function, the no-no zones of my domain. And then we will do what Bruno suggested. Once we know what we can't have, we exclude those x values from the domain. And you'll remember we wrote this more often as in set notation, or not set notation. Yeah, no, set builder notation. I was right the first time. All x such that x is not equal to, and then we list those numbers. We're going to do some examples so we get some practice and see what this looks like. We've done it before. We're going to do it again. So for my example, I want to find the domain of the function f of x equals x plus 3 over x squared minus 9. I know that's a rational function because it's a poly on top and it's a poly on bottom. That makes it rational. So we start with all real numbers. We find the zeros in the denominator. So we need to answer the question, where is x squared minus 9? 0. We can solve this a couple of ways. We can solve it by factoring, or we can solve it using algebra. Do we have a preference? Suggestions? What should I do? Algebra, so what should I do for the algebra solution? Deal with the minus 9. So add 9 to both sides. X squared equals 9. Okay, what next? Square root. Perfect. We undo squares with square roots. We know that when we take the square root of a number, we pick up a plus or minus. And I know the square root of 9 is 3. Plus or minus 3. Am I done? No. Very good. I have to write the statement of the domain. What does my domain look like? So using set builder notation, because I'm lazy. Is it a question, Bruno? You think you know? What am I going to write? Very good. All x such that x cannot be plus or minus 3. Perfect. So all x such that x is not equal to plus or minus 3. You can also write this in interval notation. We're assuming the whole number line works, and I just want to exclude -3 and +3. So starting at the far left edge of the graph, that starts way down at -infinity. Where do I run into my first problem? -3. Good, coming from the left. First thing I hit is -3. So round bracket, because I don't want to include -3. I'm excluding it. And then I'm going to join that with a union to the next section of the graph, which picks up just after -3. Where do I hit my next problem in the graph? 3. Perfect. Round bracket or square bracket? Round. Good. I want to exclude 3. So round. And then I join that with the union. Pick up just after 3. Do I have any more problems in my graph? No. So this smooth sailing all the way to positive infinity. Yeah. Either of those expressions works. Whichever one is easier for your brain to wrap itself around. Yeah. I like the set builder notation in this case because it's easy to write not equal to -3 positive 3. And I'm lazy. Very good. All right, I'm going to put another one up there. I want you to try it on your own because it's good for you. All right, I'm going to pop about 90 seconds on the clock. I want you to try that in your small group, and then I'm going to call in some people for some help. Yes, Bruno? You don't have to write the bottom one, right? Either one. Correct. Example for the top one, I want to leave this drawing, and that bottom one just confuses me. Then stick with set builder notation. Yeah. You only have to use one or the other. What? Yeah. Good. Mm-hmm. Multiplying to C and adding to B. So multiplying to 5, adding to 6. Don't judge me. If we can't square root 5, then what could we do to 5? Because I want to get rid of like x squared. I can't square root that. So we're looking for zeros of a polynomial. We go through our checklist. Is that polynomial factorable? How do you factor it? Or the x game. Yeah, it's probably easier that way. Yeah. Okay. Let's go through our processes. We assume all real numbers, and then we look for problems. Can I get a show of hands who can tell me where the problems are? Somebody who hasn't spoken yet today. I've got a couple of talkers up in front, and then a whole lot of quiet people. Okay. Make me do it the hard way. It's fine. That's fine. Yes. Gerardo. What should I do? Thumbs up if we agree. I'm getting thumbs up. Very good. There was another way we could write that. Did anybody use set builder notation? I think Marissa. Did you use set builder notation? What'd you get? Come on, pen. There we go. Curly brackets. Oh, I see what you're saying. In factored form, there wasn't anything outside of these binomials, and so no, we wouldn't pick up a 0 at 0. Good. Same values, different form. Notice in this set builder notation, I listed them in the order they show up on the number line, which is generally good practice. So -5 is further to the left than -1, so it came first. Good. So skills from the last couple of weeks, just finding zeros of polynomials and then excluding those values from our domain. Good. Very good. Okay. Let's move on to the next thing we need to worry about, which is if we go back to this graph that we started with, this graph has a very important feature. At that 0 in the denominator, for our reciprocal function, x equals 0, there is this vertical line that the function doesn't cross. Does anybody remember what that's called? Asymptote. Very good. This one is a vertical asymptote. So x cannot be 0. That's where we get a vertical asymptote. We're going to talk about how to find those, along with something that's related called a hole. And we're going to do that by looking at the two functions we just found the domain for. But before we do that, let's talk about the process of finding vertical asymptotes. Yeah? Yes, Bruno. What? Okay. Bye. Good luck at your game. Yeah. Yes, to find vertical asymptotes, which is fun to say, but sometimes hard to write. To find vertical asymptotes. We're kind of finding the same thing we were with domain. At some point, we're going to have to do to our rational function what we did to find the domain. But we're going to do things in slightly different order. So first we are going to factor both the numerator and the denominator. And this has to do with asymptotes and holes. Factor the numerator and denominator. We've been practicing that last couple weeks, right? Factor those polys. Second step is find the zeros of the denominator. In other words, do that first part of finding your domain. Where are the problems in the denominator? Where are my no-no zones? We need to find those. So often we will find vertical asymptotes and the domain at the same time because the domain process is step 2 of finding our vertical asymptotes. Step 3, we are going to reduce our rational function by canceling any common factors in the numerator and denominator. If I have an x plus 5 on top and an x plus 5 on bottom, I'm going to cancel those x plus 5s and rewrite my rational function in its reduced form. And at this point, I can now identify my asymptotes and my holes. in my reduced rational function, any zeros that are still in the denominator form vertical asymptotes. And I don't know about you, but I don't want to have to write those words out every time we talk about them today. So from here on out, vertical asymptotes are going to be VAs. Yeah. Yeah, I agree. Not for today, there isn't. So in the reduced fraction, any zeros that are still on the bottom become vertical asymptotes. The zeros that canceled out become wholes. Wholes are what they sound like. My curve is going along the graph. I have one ax value that I cannot have. I get a little empty circle, and then the curve keeps going. Like a hole in my graph. Yeah, a hole in my graph. Hole in my graph. I know they are, because the English language is weird. You will see a different phrase used for these. Your book is going to use a different word. They are going to call these removable discontinuities. We have to scooch you over. Discontinuities. Spelling is hard. When you go and you take calculus in college, there are things that we can do math-wise at removable discontinuities that we cannot do at vertical asymptotes. Things like limits, which are cool and fun. Yeah. So in this class, I'm okay if you use the word whole. I know what you're talking about. But when you see the phrase removable discontinuity, that's what a whole is. What I would like to do is practice doing this. And we're going to start with the two graphs we've already looked at, the two functions we already looked at. Don't shake your head no. That's the only way we get better at it is practice. Do you want to do the homework without the practice? Yeah, no, we don't. Do the practice first. Okay, so if I remember correctly, our first function was f of x equals x plus 3 over x squared minus 9. Is that correct? Nobody's paying attention, but nobody's arguing with me. I'm going to assume that was correct. Good, thank you, Liz. Okay, so we're going to go down this step list. First step. What is that first step? Wrote it down on your paper. Brandy, what's the first step when we're finding vertical asymptotes? Very good. Factor numerator and denominator. I want to factor this bad boy. Numerator is already factored. Can't do anything with that. Denominator matches a factoring pattern. Difference of squares. Very good. And you'll notice that matches the answer we know is coming in step 2, because we previously found the zeros of the denominator when we were finding the domain. We know we had zeros at -3 and +3. Yay. So I'm going to note that down. I know I have zeros at x equals -3 and x equals positive 3. I want to classify those as either a vertical asymptote or a removable discontinuity. That is the goal. To do that, I'm going to reduce the rational function by canceling common factors. I'm going to look at what's left. What cancels is a whole. What's left is a vertical asymptote. So let's reduce. In my rational function, in factored form, what cancels? X plus 3. I see one on top. I see one on bottom. Therefore, which one of those does that correspond with? X plus 3 means x equals minus 3. Yeah, that's this guy here. He canceled. Therefore, he is a removable discontinuity. He is a whole. The guy that's left, x minus 3, which gives me a 0 at x equals 3, is a vertical asymptote. We can check this with our graphing calculator. I would like everyone to get out their big fancy graphing calculator. It's dead. Do you have your charger with you? You have to promise to give it back at the end of class, because that's my personal one. Yours is in your locker. I'm not sure this is desperate enough that you need to do the key punches on your own, but make sure you're looking on in Marissa's calculator so you can see what's going on. Nothing. Just get it out. You got it out and it's turned on. That's great. All right. Quick review. How do we enter a function to graph it on the calculator? What button do I press? Y equals. Very good. So you're going to press Y equals when you go to type this on your calculator. Calculators are dumb and they suck at order of operations if you're not very explicit. Please put parentheses around the numerator and then hit the divide button and then put parentheses around the denominator. Otherwise, you will not get the correct graph. Yes. Well, not a bad graph, just the wrong graph. It's not inherently bad, it's just not what we want. In red, while you are graphing that, I am going to draw where I think my asymptote is. And we think we have an asymptote at positive 3. So I think 1, 2, 3. 1, 2, 3. You can press graph, yeah. If your graph looks funny, press zoom and select Z standard or zoom standard. And that will recenter your graphing window with the origin in the middle and a reasonable scale on the X and Y axes. And the question is, do you see a vertical asymptote at X equals 3? Do you see a hole at X equals negative 3? Mr. Jollo speaking. Hi. Okay, I'll send him down. Bye. Eva, your mommy's here to pick you up. I know. We're sad. We're sad you're leaving. All right, so how to check that I have a hole at negative 3? You're going to press second. Follow? Second. And then trace. And that takes you to the calc menu. And you want to choose value. And it's going to ask you, what is my X value? You're going to enter negative 3. And I see Marissa following directions, and I'm going to ask Marissa what she sees on her calculator screen after she does that. Does that. Y equals blank. Good. Y equals blank means I do in fact have a hole in my graph. There is no y value that goes with x is negative 3. So it does not draw the hole, but if you check the value, you should get a blank for y. That's how you can verify you did that correctly. And I'm assuming your graph looks something like this, with a hole that should be right here that did not show on your calculator. Yes? I see some nodding. Good. Good. Vertical asymptotes help us suss out what our graph's going to look like. Let's try another one.
Is there supposed to be nothing for y when I put a negative 3?
Yeah, because we expect a hole there. Hole means no y value. Yeah, that's exactly what you're supposed to see. That's verifying we have a hole where we expect it to be. All right. Next example, f of x equals x plus 5 over x squared plus 6x plus 5. We just found a domain for that in one of our previous examples. Julie, what's our first step if I want to find my vertical asymptotes? Excellent. Factor numerator and denominator. X plus 5, x plus 1, x plus 5. Second step, Jordan. Perfect. Where are my zeros? I know I have two of them. One at negative 1, one at negative 5. Because we found those when we found the domain. We had to exclude them from the domain. You said, oh. Next step. Next step, step 3. You said it right. I just couldn't really hear you. Very excellent. Cancel those common factors in the top and bottom. Perfect. So what common factor do we have here? What cancels? X plus 5, x plus 5. Good. So the x plus 5 factor is the x equals negative 5, 0. The term that cancels is the whole. I have a removable discontinuity here. The 0 that's left, which is the negative 1, 0, is the vertical asymptote. Oh, the negative 3 factor, x minus 3, when we solve it for x, we get, it changes the sign. Yeah. Yeah, changes the sign. Okay, you're going to practice your graphing skills. I want you to graph it and verify that we do have a hole at x is negative 5. Oh no, I broke my calculator today. Oh, funny face. Can I get a thumbs up when you've got it graphed and you've verified we have a hole at x equals -5? I see Megan nodding. So we go second, trace, and then enter to select value. And then we enter -5. And then enter. And notice it's not giving us a y value because the graph doesn't exist there. Okay, looking at student calculators, I see a graph that kind of looks like this. And we know we have a hole at -5. Is that what we're seeing on our calculators? I see some nodding. Yay, very good. Yes, Melanie. Oh, gotcha. Okay, so you have probably a slightly different version of software than some of your classmates. And so what the graph pen is doing is it's dragging its pen upward vertically as it sketches that graph instead of stopping the pen where the asymptote is. So when you see weird jumps like that, that means an asymptote on your graph. Yeah. Because other than that weird section where the asymptote is, the rest of the graph matches, other than when it cuts out because it gets too steep, which is right here. Yeah. Remind me at the end of class, we can talk about, I think, how to fix that. Okay, there's one more thing I want to talk about today, and then we should have plenty of time for homework. Yeah? And that thing is the other feature of this graph that we haven't talked about. All the graphs we've seen so far also had another type of asymptote. Horizontal asymptotes, HAs, very good. And so far, all the graphs we've looked at had horizontal asymptotes at the x-axis. That's not always the case. So we want to talk about how can we predict where those horizontal asymptotes occur. Because if I know where the verticals and horizontals are, I pretty much know what my graph looks like. Those asymptotes form the features of a rational function. So let's talk about how to find the horizontal asymptotes of a rational function. This is slightly different than what's in the book, so I want to be very explicit about what we're looking for. That is a lot of water, Gerardo. You are very well hydrated. All right. So first step is we want to make sure that both the numerator and the denominator are written in general form. What? Yeah. It's a block day. We got a lot of notes. Welcome to college math class. Remember that general form means biggest exponent first, and then exponents in decreasing order. So if I'm looking at a quadratic, I have my x term first, and then my x term, and then my constant term. Biggest exponent first. The reason we want both of those in general form is the second step is I want to identify the leading term in the numerator and denominator. Identify the leading coefficient and degree. And if they are both in general form, that should be the thing in front in the numerator and the thing in front in the denominator. Easy to pick off. Remember that the degree is the biggest exponent. The leading coefficient is the number in the very front of the polynomial. Yay. The reason we're doing that is the relationship between those things tells us where our horizontal asymptotes are. I have to remember the rules. I'm pretty sure I know that, but I just want to be sure. All right, so once we have done this, we are going to compare. And ideally, we fall in one of three cases. So case A, the degree in the numerator is smaller than the degree in the denominator. All of the examples we've done today have been in this category. Our reciprocal function had a constant over an x. Both of the functions that we worked with for vertical asymptotes had an x over an x squared. Numerator had a smaller degree than the denominator. When that happens, we have a horizontal asymptote at y equals 0, also known as our x-axis. That was why all of the graphs we've drawn today have horizontal asymptotes at the x-axis. They all fall in this category. And that's true regardless of what the degrees are. I could have a degree 1 on top and a degree 100 on bottom. Horizontal asymptote at the x-axis. A degree of 2 on top, a degree of 3 on bottom. Very small difference. As long as the top is smaller degree than the bottom, y equals 0 is my horizontal. If the degree of the numerator is equal to the degree of the denominator. Ooh, come on. Denom. We get a horizontal asymptote somewhere other than y equals 0. Specifically at y equals the leading coefficient of the numerator over the leading coefficient of the denominator. It's a lot of writing. When we do it in practice, it's just two numbers, which is why in step 2, we identified both the degree and the leading coefficients. I need them here. Oh yeah, no, we'd be here all day. So degree is equal on top and bottom. I just want to pick off the leading coefficients. It's a constant. It's going to be a nice horizontal asymptote. Leading coefficient. We have a third case to consider. And that third case is the degree of the numerator is bigger than the denominator by 1. Top is 3, bottom is 2. Top is 5, bottom is 4. They are different by 1 exponent. Okay? Top is bigger by 1 exponent. In that case, instead of a horizontal asymptote, we get a slant asymptote. That slant asymptote is going to be a line, and to find that line, we are going to divide the numerator by the denominator. My asymptote is the quotient when I divide. Sounds gross, sounds weird. We're going to do a whole bunch of examples to give you practice. Yeah? Couple more minutes. You guys got this. Okay, let's do some examples. So, first one says, find any horizontal asymptotes for f of x equals x squared plus 2x minus 3 over 3x squared plus 6x minus 15. Gabriel, when finding our horizontal asymptotes, what's our first step? Very good. Are these in general form? We have disagreement at that table. So what is general form for a polynomial? Can somebody describe it in words? Good. So that ax squared plus bx plus c. For a quadratic, that's standard or general form. In general, it means biggest coefficient or biggest denominator first, and then decreasing order. So squared, linear, none. Fifth, fourth, third, second. Okay. Good. So those both match that pattern. So I think I agree with Gabe's original assessment, which is yes, these are in general form. That's perfect. Megan, what's step 2? Perfect. Identify leading coefficient and degree. So in the numerator, my leading coefficient is equal to 1 because it's missing, and my degree is equal to 2. In the denominator, my leading coefficient is 3. My degree is equal to 2. Does everyone see where that's coming from? I see some nodding. I don't see any tears. That's a good sign. The next step, we use the relative degrees to put us in one of those 3 categories. This one, degree on top, degree on bottom are equal. Yeah. When they are equal, Where is my horizontal asymptote? Raise your hand if you remember. We just wrote it down. Everybody should remember. Jade, what's our horizontal asymptote look like if those degrees on top and bottom are equal? Did you write it down? Very good. It's that ratio of leading coefficients. Perfect. So y equals, and we wrote down our leading coefficients. Numerator was 1, denominator was 3. Horizontal asymptote at y equals 1/3. Done. 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 Yay. That's it. That's it. No. Yeah, way easier than the verticals where we had to like factor and cancel and figure out whether it's a vertical asymptote or a hole. No, horizontal asymptotes, way easier unless the top's bigger than the bottom, in which case we got to do a little bit of math. Good. Let's try another one. You want to find any horizontal asymptotes for f of x equals x squared minus 6x minus 5 over 3x to the fourth minus 6x squared plus 15. Alan, are those polynomials written in general form? Are the exponents in decreasing order? Yes, yes, it's in general form. Perfect. Second step. Alex, what am I going to do? Second step. Perfect. So leading coefficient and degree for the numerator, and then leading coefficient and degree for the denominator. I know how to spell. So we'll start with the leading coefficients. Julie, what is the leading coefficient in the numerator? 1. Perfect. What's the leading coefficient in the denominator? 3. Perfect. That looks very familiar. Jackie, what's the degree of the numerator? 2. Good. Degree of denominator? 4. Perfect. First 2 steps are done. Happy face. Third step, we compare. 2 versus 4. What is the relationship between 2 and 4? They are both factors of 2. Which one's bigger? 4. 4 is bigger. Alligator eats the bigger number. 2 is less than 4. Numerator is less than denominator. Where is my horizontal asymptote? Cecilia, if the numerator is less than the denominator, where is our horizontal asymptote? So go back to that how-to list. We had categories. Thank you, Brandy, for sharing notes. 0, very good. Y equals 0. Looks like all those graphs we do at the beginning of class. Yeah, perfect. All right, one more, and then I'm going to give you some homework time. You probably know where this is heading if you've been paying attention. Yeah, it's good for you. Do I want to do that? Sorry, I just had a brain fart. Do I want to do that? No, I don't want to do that. I'll be nicer to you. Be nice. I'll be nice. So we want to find the HAs for f of x equals 5x squared minus 6x plus 12 over x minus 3. X minus 3. So rapid fire, yes, this is in general form because the exponents are in decreasing order. I know for the top, for my numerator, I have leading coefficient of 5. I have a degree of 2 for the denominator. I have a leading coefficient of 1 and a degree of 1. 1 and 1. Very boring polynomial. So, third step, we compare. The relationship between my numerator and my denominator. Which one's bigger? Numerator. Alligator eats the bigger number. How much is it bigger than the denominator by? 1. Well, it is both in this case. When it is bigger by 1, do I have a horizontal asymptote? No. See, Gerard going, no. We have a slant asymptote. The question is where? Good guess, but let's check. Our slant asymptote is at the quotient when we divide the numerator by the denominator. So I need to do the division. What is 5x squared minus 6x plus, why did I do that? Plus 12 divided by x minus 3. What is that? Question mark. How do we do that? No, you may not. How do we do synthetic? Yeah. That's a binomial. We can just use synthetic division. We don't need a calculator for that. Come on. So, we can do this. The divisor goes out in front. We change the sign. That becomes positive 3. I write the coefficients of the numerator in the inside. 5 minus 6, 12. Last term's going to give me a remainder. I do not care about the remainder. I want the quotient. This here is going to be my slant asymptote. So, let's do the division. Bring down the 5. 3 times 5 is 15. 15 minus 6 is 9. Yes. 3 times 9 is 27. 27 plus 12 is 39. Do not care about the 39. Care about the quotient. So my slant asymptote is at y equals 5x plus 9. Because that was the answer when I divided by x minus 3. If we graph this, I will bet money that we're going to get a graph that's kind of round and then it flattens out the further it goes because it starts approaching this line. And I would encourage you to graph it now so we can see what that looks like. You have calculators handy. I will follow along on my now broken calculator. Oh, I was so close, but it's down at the bottom. So this is up here. 5x plus 9 is steep. It's crossing at positive 9. And when I look at that graph, it's kind of steep but rounded, and then it flattens out on this side. Is anybody else kind of seeing that graph? I'm getting one confirmation from Bruno. Did anybody else see a graph that looks kind of like that? Did you try it on your calculator, or are you just blankly staring at me? What do you mean it's going to come out all pointy? Yeah, but this one doesn't have a vertical asymptote quite like the others, so try it. Try it. Give me a thumbs up if you also got something that looks like that on your calculator. Some of us have gotten lazy. I'm getting a thumbs up from Brandy. I'm getting a thumbs up from Jade. Thank you. Thumbs up from Lucero. I don't know if she actually means it or she's just giving me a thumbs up to get me to go away. That looks like a bright calculator screen. Alan agrees. He just didn't tell me he agreed. Good. Very good. So, an important lesson before I set you loose. When you are finding asymptotes in holes, you have a graphing calculator. Check your work before you slap the answer into Desmos. Yeah. The math will get you the exact answer. The calculator will verify it's correct before you put it in Desmos. There are two things we haven't talked about that were on our agenda, which are x asymptotes and y asymptotes. Not asymptotes, asymptotes, intercepts. X intercepts and y intercepts. We got a preview of that during the bell ringer. We're going to talk formally about them tomorrow, and then I have a small matching activity for you. You have about half an hour of time to work on homework 3D. You also have time to work on any late homework that you have, because the cutoff is October 10th, which is next Friday. All right, I'm going to come around and answer questions. Please use this class time wisely.